what you did on Tuesday, is let's find the acceleration of gravity. Now, based upon more complex experiments, it should be 9.798 meters per second squared. Let's see how close we can get. So if you have the ability to time to 1/100th of a second, then please get out your phone, watch, or whatever you happen to have. We're going to do this several times. And something that will make a loud noise, I think this will. Yep, all right. So what's going to happen is, let's see, do we have timers? Okay, I see a couple people with their phones. I'm assuming that they're timing. So I'm going to drop it 1 meter. I'm going to go 3, 2, 1, drop. When I say drop, I'm going to let go. So presumably you're going to start at that time. And then you stop it when it hits. All right. 3, 2, 1, go. All right, so times?
0.66.
0.66.
That's what I got.
0.69. I got 0.68.
Wow, that's a nicer cluster than I was expecting. All right, so the average is 0.6725. No, that wouldn't make sense. 0.675.
Yeah, that's right.
Okay. So my time in seconds. Because it fell from free fall, I know that the distance traveled is equal to 1/2 times gt squared using Hewitt's formula. And so I have a distance of 1 meter is equal to 1/2 times g, which is what we're trying to find, times 0.675 squared.
It's 2.5.
625. Wow. Thank you.
No, 6.725.
Oh, I think I had it right the first time. 6.725. Thank you. First, I'm going to multiply by 2 just to get rid of the 1/2. So this becomes 2. Let me write it up higher so that you're not looking through somebody. 2 is equal to g times 0.6725 squared. And since I'm trying to solve for g, I need to get rid of this thing over here. And so divide by that thing on both sides. And so g should be 2 divided by 0.6725 squared. Place your bets before someone tells you what we got. I think the largest value we've ever gotten doing it this way was 25 meters per second squared. And we're only squaring the denominator.
I think it's 4.4, but I'm not sure.
We got
That's what I
4.4.
got.
Got a couple 4.4s. Units?
Meters per second squared.
Yeah. All right. So, why are we so far off? What would you speculate is the problem?
What do you mean, like 9.8?
Yeah, right. Why is it not anywhere near, or why is it less than half the value of the accepted?
They may not have measured from a meter. They might have dropped it from like a greater height.
Oh, why is ours off, not as why is theirs better?
Oh, my bad.
No problem. You can just sort of flip it and you have the answer, but yes?
Because it was, experimental error. All of us, we couldn't time exactly the exact second when it hit.
Why not?
Because we're just not that fast.
Human reflexes do play an important part here. Galileo was trying to find the speed of light, and basically made the assumption that human reflexes were a constant. So he'd shine a light, and then someone on another hill would see the light, and then shine the light back, and they time how long it took for Galileo to see the light coming back. And then he had the assistant go to a farther distance, and they did the same thing, figuring that the human reflexes were the same in both cases. And he came to the conclusion that light is very, very fast. So, human reflexes are indeed a critical thing here. So, let's take it the next step and drop it from a greater height. Sort of going along with what Bailey was suggesting, that they probably did it from a bigger height class before. stable than a rolling chair. I think that's about right. Move it. Are those meter sticks relatively vertical?
No.
All right. What do I need to do?
Go that way.
A little more.
Go. Oh,
Or move
you're
the
pointing in
bottom
different
up.
The
directions.
bottom
The
one
bottom
needs to go that way.
toward you.
Oh.
Yes, that's
there you go.
perfect.
Is that
That's,
Yeah.
mm,
Yep.
But tilt the
That's
top
good.
towards the right a little bit more. That's better.
yeah, that's perfect.
all right? Timer's ready. 3, 2, 1, drop. All right, what are our times this time?
I was definitely off this time when I timed it.
1.11.
I got 1.2.
Wow.
That's it? Okay.
That's all, folks.
The average then, 1.
I just feel like that's not gonna be right.
A physics demonstration / experiment done in class? Oh, sure.
Like, I just feel like that's gonna be way off.
So 2 is equal to 1/2 g times 1.155 squared. So we get 4 is equal to, well, in essence, g will be 4 when I multiply by 2, divided by 1.155 squared. And we're going to get something even smaller than before. What you got?
2.998.
Well, it's jumped farther up. Of course, the acceleration of gravity was less. Wow, I was not expecting that to happen. I was expecting to get better results the second time.
What do you mean better results?
Closer to 9.8.
Oh, wow.
Well,
We
there's
really
a-
messed
because-
up.
There's a 9 in it and an 8.
Oh, there we go. There we go. It's just a matter of ignoring the wrong part.
Just move the decimal.
It's all about perspective, remember? See?
Beautiful.
Wow.
I like that.
I want to do that one again. That just.
Okay, well, if we got
We're so
9.8,
bad.
Do you want me to hold it while you?
You think it's my
drop?
court? Oh, sure.
I feel like
Come on
maybe
over.
you're just trying to do.
We just need
We need to
time it.
grab that chair because I'm going to say more stable than this one.
I'm not a good timer.
Either.
Maybe you should.
Can we reflux this?
All right, let's see if we can get more than 2 people timing.
Alright, I'll do it this time.
All right. Is
I'll
it
try to
vertical?
do better. A little
Pretty-
more this way, like the middle, a little more.
Such a-
That's better.
All right.
I think it looks good. Good job, Bree.
Oh, just because you did it faster than I did.
Is that in the air?
Oh my gosh.
All right.
Oh my god.
I wish I had coordination. All right, here we go. 3, 2, 1, drop. And that was incredibly vertical there. It looked like it's hit about the same distance away from it as it was before. You don't have to hold it anymore,
Oh.
but you can keep it going.
So off.
Whatever you
What
think
do
is.
you
Such a different time.
I got 1.06.
Oh, I got 0.51.
I got 0.59.
Oh, yeah.
All right, so I heard 1.0.
Whoa, wait, what did you get?
We got 50. I got 51.
I got
0.51.
0.59.
0.59.
0.45.
0.45.
How are they so different from the first one?
Yeah, please don't use mine.
that's
We
good.
were so bad the first time.
Well, I realized
Well,
what I
any
did between
others?
them is I didn't
Like
reset
8,
it 4 times again.
Oh.
Yeah, oh yeah. No, I reset mine.
Okay.
I just suck at timing.
I say 9.5. No. Reflexes
Nine.
just don't respond. It doesn't.
Nine
It
doesn't
doesn't
do it.
do.
All right.
I know it's like, I heard
All right, so what we're going to do is we're going to use these, we'll get some answer, then we'll actually see what it's supposed to be, assuming 9.8 instead of 9.798. And then we'll actually use some electronics to hopefully come up with better answers. I say better answers, you know, I'm basing a judgment there. Answers more in line with what is generally accepted. We do have to remember that there are a whole lot of theories that were believed for 2,000 years that suddenly got trashed by the time Newton came along.
0.674.
0.674. And so G will be twice the distance, so that'll be 4 divided by 0.674 squared. Now we should get into something closer.
8.8.
8.8.
Hey.
Hey, that's pretty good.
I assume they were joking in retrospect.
I wasn't joking, that's really what I got.
I mean, it's tough. I've also noticed differences between those who wait for timing it when they hear it, or they're watching it and they stop it when they see it hit. And that also can play an effect here.
I feel like it'd be better if you closed your eyes and did it at the drop and at the.
Well, it takes a
I
little
feel like
bit
you
for
can't really
sound to
dispute
travel.
that.
All right, so if we actually, let's see what the theory says it should be. So the distance, or 2 meters, 1/2 times 9.8 t squared. So I'm going to multiply this first, so that's 4.9. 2 is equal to 4.9 t squared. First we get rid of the 4.9. And so t squared is equal to something slightly bigger than 0.4. 0.4.
0.40816, yeah.
And then, so the time is the square root of 0.40 yada yada yada. And the square root of 0.40816. 0.638. Looks like.
I would round the 8 to a 9 if you want.
Or the 8 would be a 9.
So looks like whoever had 0.59, congratulations on being closest.
That's me.
Wow, you should get an
All right, so let's try to do this slightly more efficiently. How many of you have dealt with parabolas in math class? They definitely, somewhere around half. Okay. If something's in free fall, it should actually, the graph should look like a parabola. Parabola basically looks something like that. And so if we just think about it, it's part of a parabola. So if something is falling, it starts out, if this is position versus time, I should specify, position versus time to look like a parabola. It starts out slowly and gets faster and faster as you go. The formula for a parabola would be x is equal to some number times t squared plus some number times t plus some final number. This right here is known as the quadratic term. If you've ever heard of the quadratic formula, that quadratic comes from the fact that you're dealing with a squared thing. It always seems odd to me that quad, which means 4, is associated with squaring, but it is. The coefficient here is 1/2 g. So all I have to do is use the motion sensor, have it drop, do a position versus time graph, look at the plot. The LabQuest will tell us what the equation is, and we just take this number in front of t squared, and that's equal to 1/2 times g. So let's find out what we get that way. I don't have to drop it as far, but I do have to make sure that it's actually in the stream. All right, so I guess this side over here is the best vantage. Is this parallel to the ground?
Yes.
Okay. I want to do all right, I'm going to do 50 samples a second. I would do more, but 50 is the most it takes with the motion sensor. And let's make the duration longer. 30 seconds, and then I'll zoom in. Okay. Well, this takes a minute to heat up, warm up. All right, so I'm going to start it. I'm going to put this into the stream, and then I'm going to let go. I'll move my hand out of the way. And now we get to see what this looks like. Can you see it well enough?
Yeah.
All right. So taking a look at the whole thing, you got that big spike there at the beginning. Yeah. So that big spike at the beginning is because originally it was looking at the ceiling and then I stuck something in front of it. And also, that's bottom one's velocity, so why don't we just look at the position graph, because that's what I care about. Show graph. All right, so we have some funky stuff going on here. I was actually looking at the ground. So I was looking at the ground, I stuck something in front of it, and usually when it gets a shock to the system, you get something just bizarre right there. It suddenly says that something was 3 meters away, and it's impossible, really. That's not 3 meters to the ground. When I actually dropped it, it was over this region right here. So I want to zoom in on that. And notice we have part of a parabola here, basically running from there to there. Now, there's got this sharp point right here, in this region right here, and that's because I had the ball too close to the sensor to start out with. Because anything within 17.5 centimeters or so is not going to be acknowledged. Being 0 centimeters and 17 centimeters is the same thing to the LabQuest because of the wavelength of sound that's being shot down. So what we want to look at is the region where, not the beginning or the end, but we'll take the middle part, analyze, curve fit, position, like there's a choice there. If you'll notice that there's these brackets right here, oh, you can't see it, all right. You got the bracket here and the black bracket here. It's going to do a curve fit based upon those two, all the points in between those two brackets. The cursor is not the same as this one. And then I want to do a quadratic fit. And if you'll notice that right here, we have the coefficient of the squared term. Now they're using y and x just because of default, but this y here is really position, and the x is really time. But we end up with a coefficient to be 4.8. 4.8448. And g is going to be twice that. $9.689.6. Getting closer. I think I'm up with that right. There is another way that I was going to do. I don't want to eat up more time for it, but I will talk about it. Oh, there it is. It's an acceleration strip. Basically, the black lines are evenly spaced apart, and then you drop it through a photo gate, and it will tell you, basically, the photo gate says when light will go through and when light won't, and so you get exact timings of, as this thing falls, the exact timings of when light passes through and when it doesn't. And then you can do a plot of position versus time, since you establish something as 0, and then you just mark off your positions. It light passed through this one at such and such time, it passed this one at such and such time, and so on. And then you can curve it in theory. There are other mathematical techniques as well, but that's another way of doing it. And I think I did a very quick and dirty demonstration in one of the videos with this. I did about 5 trials until I got a result that was good for video, which is not the way science is supposed to happen, but I at least wanted to demonstrate the point. But that one also, when you're dropping it, you need to make sure it drops straight down. If it's just slightly off, that's going to throw off your results, or my results in that case. All right, questions before we talk about the lab from 2 days ago? All right, so in the remaining time, you got an hour-ish. I want you to either work on the lab that you didn't finish, or if you finish it at home, give yourself a chance to actually test if what you thought was right is actually working out. And so lab quests are here, motion sensors are here, phase shields are here, and as always, rejoice. It is physics. All right, so Haley and Hannah were not here on Tuesday. Anyone else not here on Tuesday? All right, and so there are some people. So Stephanie is not here. Anyone who's here on Tuesday who is not here today, other than I'm pretty sure she was here.
The girl with Sabbath?
Yes.
Yeah, she was here.
All right, and is there a group of 2? All right, so I guess Abby and Mike work together? All right, so who was Stephanie with?
Yeah.
Oh, you're a group of 2 because Stephanie's not here. All right, so Haley, Hannah, one of you joined that group of 2, and the other person joined a group. I guess a group of 3, because that's what we'll off with. Start with Joyce.
So we're just continuing the lab from Tuesday? So we're just continuing the lab from Tuesday?
Yes, continue on the lab from Tuesday.